Hi, Professor Jed Buchwald. Thank you for being here. Professor Buchwald is Doris and Henry Dreyfuss Professor of History at Caltech. He was previously director of the Institute for the History of Science and Technology at MIT. He's a MacArthur Fellow, 95, was elected to the American Philosophical Society in 2011. Professor Buchwald graduated from Harvard with a PhD in 1974 with a dissertation concerning the history of electricity and magneticism. All right, Professor, I'm thinking we can start off by talking a little bit about the history of science and how we got here today from the, so to speak, Stone Ages, how we're able now to communicate wirelessly, how we're able to fly, do all of these things. Is it possible to give a broad summary, or is that asking too much?
Well, I think that's sort of like giving the history of the universe in 30 seconds. So I don't think you can really do that. I mean, the world we live in now is so heavily structured by technological material that it is an utterly different place from, even the beginning of the 1800s. Even though by the beginning of the 1800s, a good deal of the way in which we now do science had in fact already been strongly developed, if not all the theories, the techniques, and so on. But that was a world of horse-drawn carriages, no electricity, and so on. So we live in a completely different world, and the development of technological structures, although bound up with scientific development subsequently and vice versa, nevertheless has its own separate, if you will, logic, which is not directly an implication of science itself, but rather of driving forces within socioeconomic and technological development also.
So the socioeconomic development enabled certainly the rise of the contemporary world and of all the latest innovations of science. But what about looking to science itself? Can we point to something, a change concerning maybe physical philosophy or the application of mathematics to qualities or to our experiences? Can we point to something that can really shed light on what happened in the past few centuries?
Well, there are elements of, if you will, a scientific worldview that goes back certainly to antiquity. In some respects, for instance, the very first, if you will, identifiable predictive structures grounded in some sort of mathematical and observational setup dates back to the Babylonian period, as early as the 6th and 7th century BCE. It was the Babylonians who developed an arithmetic scheme for predicting the positions of the objects in the sky. That, however, is nevertheless very different from what the Greeks did, and subsequently, although the Greeks inherited a good deal of what they did from the Babylonians after Alexander conquered the entire area. In this sense, the Babylonians did not work with models of the heavens. They had a kind of arithmetic scheme, and they were superb observers, and they observed over hundreds of years. And they could predict eclipses and so on using this arithmetic scheme. But so far as we can tell, they had no model of the heavens. The Greeks inherited a good deal of the Babylonian arithmetic system. In fact, we still have some of it today. Our clocks, our degrees, minutes, seconds, divisions are direct descendants of the Babylonian system. And the Greeks brought that together with their, if you will, penchant, the way they thought about geometric structures. And they evolved over several centuries model-based reasoning, grounded on geometrical structures, and that persisted. And in fact, in some ways, that we are the direct inheritors of that, even though the Greek system geometrically is centered on the earth at the center of the universe, but it's a highly mathematical system.
Right. So it sounds like to me that is indicative of the concept of applying the quantitative onto the qualitative, that we can represent certain experiences of ours using numbers, and consequently work with that mathematical system and use it to predict future experiences. Was that an insight that already was had in Babylonian times, or is that something that we have to place later on, such as with Bacon or Descartes maybe, or Galileo or somebody like that?
Well, I mean, there's a long period of history between the Babylonians and the 1600s, the time of Galileo, Newton, and early on Bacon. And I think you could say this, the development of a kind of mathematical structure for optics and for the motions of the objects in the sky, passing from the Babylonians to Greek models, and then under the Islamic caliphates, where there were tremendous developments, both of observation and so on. However, there's a big and fundamental difference between developing a scheme which can predict stuff in the heavens, which you can't play around with. I mean, we cannot alter the patterns of the planets and the stars, right? There's a big difference between that and building some sort of apparatus to try and investigate the way things operate, let's say mechanically or in other ways. It's the difference between an observational system on the one hand and an intervening experimental system on the other hand. And until, really sometime, you could push it, there are exceptions, in the late Renaissance, the idea that you can develop knowledge about the way things go on in this changeable world about us by making artificial devices was, generally speaking, not accepted. Once you start monkeying around with the world as we know it, the general thought dating back to the Greeks and then in the medieval period was that you can gain knowledge maybe about that apparatus, but not about the way the world really works. So the invention, if you will, or development of the kind of experimenting that we do today really dates back to sometime in the late Renaissance. And interestingly enough, it emerged first among alchemists, people who were putting chemicals together in alembics and so on, creating new amalgams and so on. Yes, they had, shall we say, in many cases, strange views of things, but they could combine, manipulate, and structure things. And that was very influential.
Right. Certainly self-interest has been a driving force and continues to be so. The desire for profit can motivate us to pursue scientific inquiry. So would you say what you described would be a transition from a deductive model of the world where, as Aristotle is said to have done, we're taking a certain view and then deducing consequences and making observations strictly through the prism of those consequences, to an inductive model where we're making observations without necessarily making hypotheses and then trying to form this world image? I think, as Newton encouraged people to do and claimed that he did, without, meaning not making the hypotheses.
Well, how shall I put this? I mean, there obviously are differences and differences. However, it is certainly not the case that anyone that I can think of went into structuring one of these experimentally built devices without some thoughts about what they're going to find. They may not know the details. In fact, probably don't in many instances. Would hold for Galileo or for Newton. For example, Galileo's manuscripts pretty strikingly show that he rolled balls, probably marble balls, down a groove in an inclined plane. Now, that's what led him eventually to his first form of a law of motion, relating how far things go in a given interval of time. But he didn't start out by thinking that it was going to please some arbitrary relationship of some kind. No, he thought that there would be a fixed relationship of some kind between distance intervals as the balls roll and intervals of time. So, for instance, what he did, and this shows you that he had something very specific in mind. He was a good musician. His father was a musician. This is a period before there were no devices to time anything accurately. But a good musician can sing very accurately, easily to intervals of a 64th of a second. He tied little pieces of string across the grooves in an inclined plane, and he started singing. You can imagine making equal intervals of time by singing. And he let the ball roll down, and he moved those strings until he heard each string being hit at equal intervals of time. And then he thought the distances would follow some sequence of integer numbers. Turned out to be the odd numbers. So he didn't start just exploring, anything. He had a very specific notion. And this is true for almost anything you can think of.
Wow. Yeah. No, that sounds incredible on his end. I think it was actually Thomas Kuhn who questioned whether he really did those experiments or simply claimed them. But I think later on it was confirmed that he did do them. But what do we say then, that any and all observations must be, so to speak, theory laden? They must be had within a paradigm, a broader worldview that carries suppositions that are not found directly in phenomena, in experience? Or can we truly have a purely inductive model, at least in ideal circumstances where there's no theory whatsoever?
No, you never have something that is purely inductive model where you don't know anything. You can't go in without some kind of thing. Even when you decide what you're going to measure, you've already made some assumptions about things because you're going to use certain kinds of apparatus and you're going to look for certain things. Let me come back to that, though, and go back to this question of theory ladenness. If we were to say that every observation is theory laden, that kind of leads to this notion that there is a well-structured scheme in people's minds that, they design everything around. That, I think, pushes things too far. And I think the Galileo example shows that. I mean, it's a very broad thing that he's looking for at the time. And most experiments that I can think of, except for certain ones, are not so deeply embedded in a specific theory. There are certainly exploratory experimentation in which you're looking for certain relationships, like Galileo did, or I can think of many other examples, within a certain well-defined spectrum of possibilities. And those possibilities will be, as it were, exemplified by the types of measurements you make, the kinds of instruments you build, how you think the instruments themselves work. These things are not separable from one another. So no, there isn't that, here's a fixed theory. I'm going to build a fixed instrument and that's going to tell me something. No, it's a question of what you're looking for. Now, there can be exceptions. Suppose you do have a very fixed theory, which happens to have certain mathematical structures, and there are certain constants built into that theory, like the law of gravity. But you don't know the value of the constant. So then you might build, as indeed Henry Cavendish did, a very specific apparatus grounded on your theory of gravitation to measure what the value of that constant is, which you might otherwise not know. Actually, what Cavendish did measure was effectively speaking, the density of the Earth using a balance based on the law of gravity. So there you see, you are working, but that's a particular kind of thing. Exploratory experimentation can be very different. The discovery of electric waves was more of an exploratory thing, but within a very specific framework, very specific device. And Heinrich Hertz, the discoverer, was in fact looking for certain specific relationships.
Right. And I think this can lead us nicely into thinking a little bit about so-called scientific realism, because it does seem that in contemporary kind of scientific thought, some of these observations that you put so well are not kept at the forefront of attention. And it does seem to be a common belief that we can have a purely inductive observational or observation-based science that doesn't rest on any assumptions, doesn't involve any implicit assumptions. And I think that would be a view that can be called scientific realism. And then there are those that would make those critiques. How do you feel, Professor, about so-called scientific realism? Is it naive or is it well-founded, well-based?
All right. Well, I think you have to distinguish a couple of things there. Usually, when you're talking with philosophers of science and you use the phrase scientific realism, what you have in mind is the assertion that the specific claims and the specific objects that are envisioned in a scientific theory are not just, shall we say, phenomenal models, which you can then derive certain predictions from, but that the objects in fact exist as such in the world. In other words, it's not just that we have a nice model of the atom with electrons and so on, grounded in quantum mechanics, but that such things actually exist, putting aside the issues with quantum realism for a moment and so on. And so that's one thing. On the other hand, I think what you in part were driving at is, would it be possible to generate such things in a theory by doing enough infinite numbers or huge numbers of experiments? No, I don't think it would be possible to do that. Now, somebody will come right back at me and say, well, what about artificial intelligence? And I think actually that actually kind of proves the point. What could you, for instance, conceive of doing very well with a highly developed artificial intelligent neural net system? Well, one of the things that is increasingly coming up are the modeling of protein structures. These are very complex. And it looks to be the case that by feeding lots of different characteristics into an artificial intelligence system and so on, that such a system, a neural net, may be able to come up with the protein structure that will fit these various criteria. Is that the development of a scientific theory? Well, not really in the sense that I'm thinking of. It's rather more like the intelligent measuring of a constant that you don't know the value of. You don't know what the structure of the protein is, but you feed in a lot of data Where does the data come from? Measurements of various kinds. The neural net goes out there, gathers all these things, puts it together, and comes out with a protein model. If this were the late 1700s with Henry Cavendish, he could have made, if he had an artificial intelligence system, lots of different measurements of these things moving around, fed it into a neural net, and bang, out comes the value of the gravitational constant.
Right. That's an excellent point, Professor. And I think also kind of an obvious point, but that might be easy to forget, is that we interpret the appearances that artificial intelligence and machines show to us, and that is certainly not the same thing as the machines comprehending the appearances. For example, a calculator can show us any sum, insofar as it doesn't exceed the capacities of the calculator, and yet we wouldn't say a calculator knows even what 2 + 2 is. It's a physical system that is designed to show appearances in a logical manner. So even artificial intelligence, the outputs it's giving us and the data it's working with isn't data from its, so to speak, just to put it that way, point of view. It's only to us that it is information, right? And I think that's why actually those CAPTCHAs, however they're pronounced, work to identify bridges, identify things, right? Only we can do that, as opposed to the computer, at least without perhaps further advances.
Well, I think that certainly is the case right now, but let's not push it too far. After all, let me be blunt. We are nothing but material systems ourselves. Granted, we're not built out of silicon and so on, but I see no a priori reason why it would be impossible eventually to conceive of a silicon-based system which can achieve the same levels of internal sense that we have. We don't have anything but nerve cells and body cells. So that's silicon things are built out of different stuff. But so I wouldn't push it too far. I mean, we're not in the era of the Terminator yet or anything like that, but I don't a priori see why we might not be one day, which is actually a kind of scary prospect in a lot of ways.
Right. I mean, this might be veering a little bit off track of our direct conversations, but we could say that the defining characteristic of a person is the quality of being a subject, of being an I, and everything else consequently comes across to us as an object, including nerves and nerve cells. Right? As Whitehead said, we tend to treat the senses on objectivist principles, supposing that they are really truly there, and all other phenomena on subjectivist principles, right? With, again, that distinction between primary and secondary qualities. Secondary ones are subjective, primary qualities are objective. But we can kind of turn it around and say both primary and secondary qualities and altogether all content comes to us as an object in our subjective experience. And I think if we go with that reasoning, we do not have grounds to say that any computer will ever be able to be a subject, because there seems to be a qualitative difference between a subject and an object.
Well, how would you know? For instance, I'm looking at you on a screen. There's a virtual representation of you here. I could certainly envision a time arriving when a presentation that looks like you or some other human being is conversing with me fully intelligently. How would I know? That's the Turing test eventually. How would I know that you're not, in fact, having a fully subjective experience? I don't know that you do.
Right. So here I think we would have to distinguish between a self-experience of subjectivity, whether it's called qualia or whatever we want to call it, and phenomena. The screen is phenomena. All other people come across to us as sensation. Somebody who's not sighted cannot see what sighted people can see. And yet the subject that we would be talking about isn't a sensation, it's a self-experience. I seem to know that I exist, and period. right? And then I interpret the phenomena, the sensations that I have based on my logic. Am I dreaming? Am I hallucinating? Is this a simulation? Whatever the case might be. Or is this a real person? And then I try to come up with conclusions. I might be wrong, right? There's concerts with holographic musicians nowadays. You look at it and you're like, oh, it's a real person. It's a mistake, right? It's a simulation. But the logic in itself seems to hold steady, if that makes any sense.
But, this actually touches on what I think is probably one of the most significant developments in the ongoing history of science that really occurs substantially in the 17th century, the 1600s. One associates it with Descartes, but he's far from the only one. And it's this, that from the Greeks on forward through the Islamic and medieval periods and so on, the general conception is that our sensory systems, our eyes, our feelings of touch, smells, hearing, and so on, if they are working properly, directly pick up the qualities that subsist in the world out there. When I look at something that is a shirt, let's say, that is red, I'm not seeing red in a sort of abstracted sense. I'm actually picking up the qualitative redness of the shirt that's out there. What I'm saying is there's not a notion that things come in from outside, affect our sensory system, and then somehow there's some process that goes on which then interprets those signals to create the world as we then perceive it. That notion that the world is, effectively speaking, a production by our nervous apparatus of signals that are sent to us and that our sensory apparatus perceives is a huge novelty in the 17th century. And it's one which splits for the first time, if you will, the physics of the world away from perception itself. Those two things, the physics of the world and the perceptual qualities, are bound together until sometime in the 1700s. It still slightly bound together then, but the general notion, most clearly enunciated by Descartes in that sense, is that our senses are merely instruments. And what affects our senses when I'm looking at something red, what affects my eyes is nothing like the quality of redness. This can even hold for shapes and so on, by the way, despite this distinction between primary and secondary, that it is we who interpret somehow in the mind, says Descartes. He locates the mind in the pineal gland, by the way, the signals of pushes and pulls or whatever that are acting on our sensory system. So that if you push it to its logical extreme, the world as we perceive it is, entirely speaking, a creation of our perceptual system. That is, it's what I see out there may or may not have any real relationship other than sending signals to my perceptual system. A philosopher of science, I forget his name, once wrote a famous paper on the question of what would it be like to be a bat?
Nagel.
Yeah, that's right. It was Nagel. And I think that that's a very modern way of thinking. Such a thing would not have made sense to somebody before the 17th century.
Yeah, that's a phenomenal point, Professor. We tend to kind of the assumptions that we make, the metaphysics, so to speak, kind of sinks beneath the surface, and we simply begin to assume that this is how people think and have always thought. And yet, that distinction between a postulated thing in itself or an objective world and our experiences of it, like you mentioned, probably only arose within the past few centuries, including with contributions from Locke with his distinction of primary and secondary qualities, and then Kant obviously hammered home the point that there's a thing in itself, and our ideas are relegated to the realm of the subjective. And yet we can also question that notion and question whether it is warranted to make that split between primary and secondary qualities, between things in themselves and our experiences of them. And we see if we stick with that, there's so many problems, right? What is a thing in itself? I think it was, how do you say his name? Schlick, Maurice Schlick. Schlick, yeah. He made the point that if you're looking at any object, you can look at it from an endless amount of distances, an endless amount of shades of light, right? So which one would be the image of which the perceptual image is of? Something like that, right? There's so many problems. So if we get rid of that demarcation and say that there's simply experience, right, then I think we also, going back to the prior point, might incline to the view that we do exist as subjects, right, as eyes, and phenomena come across to us, experience comes across to us, and from that we build up our world images from which we do physics. But we wouldn't then invert things and say that the postulated objects of physics, such as atoms, such as electrons, and so forth, are the real reality, and that they're more real than us or our experiences, or that because our experiences are us.
Well, I mean, if you take the view, which I think is these days an entirely reasonable one, given the explosion of work in, among other things, brain science, that we have a mental apparatus made of brain cells and so on, which definitely is receiving signals from our sensory systems, and that by probing in various ways the brain structures themselves, altering things, you can indeed alter the way in which the perceptual structure of reality is built, at least to some extent. That I come back eventually to the point that I think that at some point we are going to be walking around with automata that are indistinguishable in our interactions with them from human beings.
Right. Well, I hope not, Professor, because that does seem to be a scary world, much different than the present one, reminiscent of all those movies, Terminator, what is it, Bicentennial Man, this and that. But again, I would revert to the point that if we simply imagine ourselves as an object, I think of myself, I'm such and such person. I think of what I look like in the mirror or on a picture. And then I say that that's me, then I can easily imagine that one day there will be robots that are just like me. Why not? But if I pay attention to my own subjective experience and to the capacity to think and to reason, and even more kind of poetical things, to love, to have courage, nice things, right? I pay attention to these things. I think, again, we have grounds to suppose that cannot be ultimately reduced to some of the objects in our experience, such as go by terms that we've used already: atoms, matter, silicon, and so forth.
Well, of course, you're touching on the problem of consciousness and so on, which is a very tricky problem. But again, I would say this: whatever and however it is that consciousness emerges as a result of the structure of a complicated system made of cells like the brain, I don't see why it can't also emerge in a different material instantiation.
Right. Well, then that again, that statement, we're kind of veering off track, but that statement itself, again, hides the presuppositions that we are talking now about. We're already assuming that consciousness is an epiphenomenon of the brain and of cells. One thing we could say is that even the notion that there is something called consciousness might have come about also only in the past few centuries, with Descartes' split of mind and matter. Who says that there is mind or that there is matter? These different philosophical systems, so-called monism, that would have it that there's a single substance of whatever sort, such as say Spinoza's system. So we could go in that route, or we could say, I don't know, consciousness, but I exist, and I can feel and understand that I exist, and then I have different experiences of sight sensations, of touch sensations, and what we would mean by the term brain would necessarily be some of those experiences and sensations of ours. Again, we can't just treat the brain on objectivist principles while treating everything else on subjectivist principles.
Well, I must say that I tend to sit with my colleagues in neuroscience on that question, because they are increasingly successful in generating and understanding the ways in which perceptual structures work, and the way in which the world as a result is built up out of it. And I think that they continue to be successful at that. We've just here at Caltech built an entirely new neuro institute to probe these things and so on. And unless one somehow thinks that there is an ineffable spirit floating around, which is non-material out there in the world, that is responsible for the existence of consciousness and so on, it seems to me that we sit with the increasing success, even within the world of biology and neuroscience, of what's going on there. It's a question that will never be definitively answered, but, and I hope I don't live long enough to see this, but if the day comes around when I'm sitting at a table conversing with a robot and cannot tell, no matter what I ask this robot, that I'm not talking to another human being, another conscious entity, then I think these questions of deep philosophical significance become quite passé.
That is certainly a view to take, Professor, and it is a kind of a transactional view. And I think in the Turing test, the idea is that if I can't distinguish whether it's a computer or person, I say it doesn't matter. And yet, I think that we can still, while noting, as you said, that our experiences are regulated vis-a-vis logical relations concerning our body, concerning the brain. I drink some coffee, I feel one way. I drink some alcohol, maybe I feel another way, sure. But that still would be an empirical question, not a philosophical question concerning the primacy of the subject versus the object. I do so say, but yeah, I think
that, of course, is you're telling me that you have such experiences, but how do I know that you do? Of course I don't.
Right. The starting point is always our own self, and then it's so far as I see myself in another.
I have to go with what one experiences and what one can do in the world around us. But anyway, this whole break between the notion of a world which is a creation subjectively out of sensory signals and so on, and a world which exists as such separately with its full set of qualities is pretty much a new notion in the 17th century. Nobody that I know about thought anything like that before. I mean, an Aristotelian scholastic would say, well, you can have illusions and so on, but that's because that just means that your eyes or your hands or whatever are not operating properly, or you've drunk too much or something. You've perturbed the ability of your senses to pick up the real qualities of the world.
Right. I think some of these assumptions that we're now walking around with, again, are so implicit. We don't pay them mind, which can bring us to Thomas Kuhn, which I believe you had an association with him and his work concerning paradigms and scientific revolutions. Can you comment a little bit on Thomas Kuhn and on his insights there?
Sure, yeah. Well, when I was an undergraduate at Princeton way back in the 60s, I was his research assistant. And then over the years, we were very close, especially in the years I was at MIT. He died in 96, but so he would come over all the time. do think that the way in which he thought about the development of science and so on makes a lot of sense, but it's a much more complex and deeper structure than can be captured just in something like paradigm and whatnot. And he developed it more elaborately as time went on. And I think that the underlying core of the way he thought about things has at least two significant aspects to it, which are a little hard to put fully into words. And they're these, that on the one hand, what constitutes a scientific scheme in its fullest sense is not something that can be expressed in anything like a set of structured sentences. And what do we mean by that? It means by that is there is too much that goes into such a thing that cannot be captured in a kind of axiomatically structured system. He would often say, if you want to see how, well, all right, let me back up. How do we train scientists or mathematicians for that matter, but let's say physicists or biologists for a moment. Take physicists. You're here at Caltech. Everybody has to take physics 1 and 2, even if they're going to be majoring in chemistry or biology, so on. Now, how do we train them? Well, we have textbooks and we have labs and so on. But suppose you imagine a kind of training system in which I just gave you a set of textbooks which just told you, let's say, how quantum mechanics works. Would you be able then to reasonably efficiently solve complicated problems that arise in quantum systems? I think the answer to that is almost certainly no, because the way we train people is we have that, but we have something else. We have problem sets. And the way in which you learn how to work the system is by solving the problems. And there's all sorts of tricks and techniques that go into solving a problem, setting up a model system. What's the best way to do it? What do you handle? What kinds of approximations do you make? There's all sorts of things that are a lot like learning how to ride a bicycle. You can't really express it fully, but you get the idea by successfully solving problem after problem after problem. When the professor then corrects and says, yeah, you did this pretty well, but you know, you really have to think about maybe doing it a little bit this way instead. And you do that a lot. And then you learn how to become a practicing scientist in that sense. Interestingly, if we go back to the Babylonians again, on these clay tablets, we do not actually have, strictly speaking, anything like just the textbooks without the problem sets. What these tablets actually have are only the problem sets that remain. And so that's number one. Then secondly, I think that Tom Kuhn, thought, especially towards the end of his life, that really the fundamental way in which a scientific scheme works and evolves is by cutting the world up in specific ways into different kinds of things and establishing presumptive relationships among these kinds of things. And that when a scientific scheme may alter over time is not so much because there's some kind of crucial experiment, and then there's a sudden flip, which he kind of originally sort of thought, but is much different from that. It's a way in which the objects that the scientist conceptually works with are mutated conceptually, and novel relationships are established among them. And one can see this historically in that when a shift is beginning to occur, the old ways of talking, the words that were used, the objects that were spoken of, a lot of the wording still persists, but it begins to take on a different kind of meaning, so that if you tried to read it the same way you would have read it before, you run into problems. One sees this in the early development of the wave theory of light in the early 19th century, in which the terminology for polarization structures altered, but used some of the same words, but they began to take on different relationships. And you had to learn how to do this bit by bit, rather than just, axiomatically writing things down.
Right. And I think that he made that point that in order to understand, let's say, the Aristotelian system, we have to really dive deep into how the Greeks thought and what the words that he used meant to him versus what they might mean to us, interpreted in light of our modern notions. Further, I think we can pay mind to the angle that, let's say, the Aristotelian worldview, right? It rose to ascendancy, whatever the circumstances there were with the Islamic world and finding the text and this and that. And it was the exclusive lens through which mainstream science viewed the world, right? And then it began to lose its popularity, it began to lose its traction, and was replaced by, again, what maybe we could call an inductive worldview with Bacon, whatever the case might have been. But as soon as it's out of commission, nobody thinks anymore to view the world through the lens of Aristotle. So is that also kind of what he meant, that we assume?
To some extent, but that there's always overlap and so on. So in the early to the mid 17th century, for instance, you do find a number of instances of people writing books in which the scholastic Aristotelian matter and form qualitative structure actually transitions with some of the same conceptual apparatus into a scheme in which the world is thought to be based on atoms and material things. How does that happen? Well, Aristotelians, scholastics, will always talk about matter and formal qualities. Well, there are, Daniel Sennert is an example of this, one of these characters in the first half of the 17th century, who would often talk about the formal qualities of atoms and so on, not just an imagery of shape and motion and so on, but rather envisioning that in some sense you can instantiate form in the atom itself. But what happens is, whereas in the Aristotelian scheme, formal qualities are mutable unless they're essential to a thing, Sennert reduces all forms to things that are permanently locked to, in this case, the atoms and whatnot. They have forms, not just shapes and so on. They have qualitative things in a certain sense. But what are these qualities? Hard to say, but they still have a certain resonance or sound, sibilance of an Aristotelian nature. Then over time, that slips away, it goes away, and you're left with something very different from it. But there is not just this sudden shift from one thing to the other. Gradually there is, and then things are looked at very differently. And you would start to talk in ways that would make no sense to an Aristotelian. But that doesn't occur instantaneously, usually.
Right. Atoms, I think, are a great example because we see references to them all the way back, probably with Epicurus and Lucretius and such, where obviously there was no microscopes, no electron microscopes, nothing like that. So this idea was come up with philosophically, right? It was convenient in the worldview that they wanted to have, and then it was resurrected. Was it Delphin or somebody like that? But in the past few centuries, And it seems that that would be an example of what Kuhn was talking about, that we have the atomistic paradigm in light of which we make observations, such as observing Brownian motion or whatnot. And until, say, the quantum kind of innovations fully take effect, and I think now there's no longer a concept, right, of a set immovable atom with qualities, right? And I think until that fully kind of transitions, people will continue to view things through the atomistic kind of framework.
Right. Well, of course, the quantum world with the quantum states and wave functions is a different issue in a lot of ways. But talking, for instance, if one sometimes envisions that in Greek antiquity, Roman antiquity, with Democritus and Lucretius, and notion of atoms, if you will, that is something like what, say, the 17th century, say, a Newtonian would think of, but it's not, because they tended to think that these atoms actually carried with them a lot of the qualities of the objects themselves. There's no notion that I've ever seen in Lucretius. We don't really know very much about Democritus except secondhand and so on, that the atoms produce, by banging into our eyes, impulses that we then interpret as colors. No, the way Lucretius talks, the atoms themselves are carrying color with them. And they slip off the surfaces of objects and they bring those colors right to us.
Right. And now it sounds incredible to say that. And I think he added also that the reason we have free will, which is necessary for full pleasure in life, is that the atoms swerve once in a while randomly. And it sounds primitive, and yet I think maybe our contemporary views of these matters may also be looked upon like that in the future, if the paradigm sufficiently shifts, right? Because as we mentioned, I think there's certainly issues with the view that there are those things in themselves, and whether the atoms enter our eyes, or we call them proton, or we call them what's the word, photons. Whether it's photons or atoms, these might also come to be viewed as simply metaphorical kind of ways of describing certain experiences of ours.
I suppose it's conceivable, but at least, you see, it is the case that anything that I can think of, certainly in the way of natural philosophy and so on, that when changes occur, there is a not inconsiderable portion of the original system that passes over into the new one in usually somewhat different form. So there's many instances you can think of that it's an issue of the transition of data from one to the other. For example, in the case of, let us say, general relativity, it's not that general relativity discarded Newtonian gravitation. No, the relationships that hold in Newtonian gravitation hold under certain approximations in general relativity. In fact, the way Einstein finally arrived at his set of equations was under the constraint that they had to be workable to yield in appropriate circumstances relationships which would be materially no different at that approximation level from those which hold in Newtonian theory. That passes over. Of course, the conception is different. We have a metrical field instead of particles acting directly on one another at a distance, but certain structural relationships remain the same. You have to be able to retrieve the Poisson equation as an implication under approximation of the metrical field.
Right. And I hear the notion of, quote unquote, saving the appearances. I think, was it Doom or somebody like that, use that phrase comes into question, right? We have these appearances, we have these regularities of experience, and then we seek to create a mathematical world image from which they can be further predicted. But does it follow from that so-called laws of physics have any more reality than simply descriptive means of our experience? Or does it follow, or are we unwarranted in making those assumptions? I think, as for example, maybe Mac claimed, or Poincare and guys like that.
Well, I think at a certain point, that question is a question which verges into an unanswerable one of metaphysics. My feeling is, I mean, here I'm at Caltech. I was at MIT before. I was trained at Princeton originally as a physicist before I decided to go into history of science. If we can structure scientific schemes which work extraordinarily well in yielding us a manipulative and predictive characteristics, then frankly, it becomes, in my opinion, just my opinion, nugatory to worry about the deepest question, so to speak, because it's unanswerable. And questions that are unanswerable, even in principle, hold no interest for practicing scientists.
Right. Well, the assumption that it is unanswerable probably is also a metaphysical assumption, right? Some would say that we can apply the tool of philosophy or of a priori reasoning to our experience and gain some insights here. Obviously, some would certainly object to that.
I suppose I don't see it unless you can measure, create instruments to do things and so on. It seems to me that A can say X, B can say Y, A says this, B says not this, and where do they come together? Not unless there's some way of measuring, testing, probing.
Right, and that is that is an excellent perspective too. We can briefly mention there. I think we will. How do you pronounce his name? We will. Willie.
William Whewell.
You pronounce it Whewell? W-H-E?
W-H-E-W-E-L-L. William Whewell. Yeah.
Oh wow, Whewell. Oh, you wouldn't think that from the spelling. So Whewell brought up the example. How would we falsify a claim that two equal weights balance each other out on a scale? We see that if we make an observation where one weight is not balanced out, one side of the scale is not balanced out, we would never say that, oh, well, I guess that two equal weights do not balance each other out on a scale. We would simply say they're not equal weights, or we mismeasured, or the scale is wrong, right? So this seems to point to the primacy of a priori reasoning as opposed to purely.
I don't agree with that, actually, because there's more than one way to make a measurement when it comes to weights and relationship also to mass. And when there's more than one way to handle something, one can use springs, one can use all sorts of different things, that they come together in a coherent fashion to yield a conciliant set of relationships, then I don't think it's just a matter, so to speak, of making a kind of a priori assumption of this, that, and the other thing. When you say weight, for instance, and you say mass, for instance, these things have meaning within a context of ways to make measurements. Otherwise, they lack meaning altogether. And that is to say, they are bound up originally with conceptions of how to make measurements and so on. Newton was extremely good at such things and often envisioned very concrete ways to investigate relationships on the basis of measurement. When he was trying to figure out how resistance occurs as bodies move or fall through liquids and so on, he did some elaborate experiments on that. Actually relates rather directly to such questions as mass and eventually weight and whatnot. So it's if there's only one way to do something, then you're probably floating around in a system in which you can make all kinds of arguments. But when there's multiple ways of doing things, then things are different. And frankly, from what I've seen historically, I think that only when there are multiple ways of getting at something do you actually have something that holds actual meaning.
What about relating, for example, Euclidean space to physical space? Isn't it so that there are multiple internally consistent systems that can equally map onto our experiences, and we have to make that decision? Or is there something concerning physical space that suggests overwhelmingly the Euclidean system?
The Euclidean space, if we take general relativity, for instance, is in fact an experientially approximation locally to the metric that holds when you're sitting in a region which, in our case, has various masses distributed around it. So it is predictable that our experience, say, of such things as the parallel postulate, that is, two parallel lines, equal distances, never meet the Euclidean parallel postulate, is deniable because you can create different systems where it doesn't hold. And in fact, according to general relativity, we exist in such a system. It's just that locally it holds.
But is there something in our experience that suggests that system, or is it an arbitrary mapping onto or applying the quantitative to the qualitative, as we mentioned?
You're talking about Euclidean geometry, Euclidean space. Well, it holds. You can make all kinds of experiments and measurements and so on, and it holds very well.
And does it suggest it at the expense of other internally coherent, consistent systems?
Well, if we're talking spatial measurement and so on, I'm not sure what such systems would be, because if we're talking, I mean, when we talk Euclidean space, we're immediately considering relationships between angles, straight lines, circles, and things of that kind. And that instantly also brings in the issue of how do you produce a line? How do you produce an angle? How do you envision these things? The Greeks worked as considered that the only really proper way of constructing things, there were only two ways to do it, really. If you're talking plane geometry, you use a straight edge and a compass. That's it. Everything has to be constructed through that. If you're talking broader regions, you can take a cone, slice a cone with a plane, and create these so-called conic sections, which is how they're originally produced. That's why they're called conic sections. These things are envisioned in terms of the constructible methods by which you can produce them.
And yet, doesn't that, at the point kind of I'm getting at, doesn't that nonetheless imply that our bounds of perception and of reasoning determine any systems that we may come up with? So, for example, concerning the ancient Greeks, the Zeno's paradox: how can a turtle ever, or how can a rabbit ever beat a turtle? Because first of all, it would have to catch up the half point of the turtle, and then the quarter point, the eighth point, the 16th point, and there's a finite amount of time, as it seems, to cover an infinite distance. And yet a solution would be that is presupposing that the quantitative here is literal and actual, that there is an absolute half point, as opposed to us simply mapping on a half point onto our kind of open-ended visual or tactile experience. Right. So if we go with that latter view, then that paradox is solved. Right. And also, as it concerns the temporal, because how can 5 minutes go by? Well, 2.5 minutes have to go by, and half of that has to go by, and half of that, and half of that. So how is time possible? But if we consider these to be our experiences, whatever they are, and then that we are reading into them and parsing them up and breaking them up according to our preferences and needs, I think that gets rid of a lot of difficulties, and yet also carries some assumptions with it. You get what I'm saying?
Well, I don't think, I mean, Zeno's paradoxes create all sorts of, but these are the paradoxes of the infinite. These are the paradoxes of continuity, the paradoxes that arise when you attempt to impose something that involves infinities on something that presumptively operates continuously and so on. And those are the paradoxes which are worked beyond through the calculus in the conception of limits, in the conception of limit structures and so on. Yes, they're difficult, whatnot. But in the case of Zeno's paradoxes, what you just did, for instance, by saying halfway and then halfway again, and then halfway again, you're cutting up a continuous sequence into a discrete set of integral sums, integer sums. This and half of it, and half of that, and half of that, and half of that. That's not the nature of continuity. That is, and the Greeks would tell you that too, even though I'm not saying Zeno's paradoxes are simple at all. People still discuss these things, but that is mixing up two different things. That's mixing up a scheme which, effectively speaking, consists of counting this and half of that, and the next step is half of that. It's an infinite set of discrete steps versus the continuous nature of quantity, which the Greeks were perfectly able to handle when it comes to magnitude. So in Euclid's Elements, for instance, there are two different theories of proportions, one dealing with discrete, what they called number, counting things, what we would loosely call integers on the one hand, and continuous magnitudes on the other hand. And they are kept separate from one another by Euclid, in major part to avoid the paradoxes of the infinite.
Right. So, but the non-mathematical, you correct me if I'm mistaken in the interpretation, but the non-mathematical interpretation of what you said would be that our experience of space and time is subjective, it's qualitative, and it's a matter of our experience. And the paradoxes only arise when we, first of all, apply the quantitative. That in itself is fine. We do that for our purposes. But when we take that to be literally true and literally there, and we could say there is no actual halfway point concerning any visual experiences of ours up and until we apply it, right? I'm flying on a plane, I look out, I point a dot for this moment, that's the halfway mark. What does it mean to say it exists in some kind of other objective way? It's only when we say it does exist in an objective way that all of those issues come up.
Well, I suppose you could certainly say that. But again, the difficulties of infinite sums and so on are non-trivial. And to really get past them, you have to develop notions of limits and infinitesimal quantities and so on. And you're in the realm of the development of the calculus at that point. But yeah, I mean, those paradoxes do arise if you start putting together and mixing things up in various ways that don't hold out there. As you know, the rabbit isn't stopping halfway, and the turtle isn't stopping halfway, and then stopping halfway again, and so on. They're continuously moving. This was a big problem, by the way, for Galileo, because when Galileo came to the conclusion that speed in a falling body varies continuously, not in discrete jumps, but continuously, then trying to prove propositions, actually the central proposition in his two new sciences, was not something easily done, because he had no easy way at this point of handling a continuously changing quantity like that. So the actual proof that he gives of what's called the mean speed theorem in the two new sciences, which underlies his mechanics, if you will, is from the standpoint of a continuous quantity is quite defective.
Continuous quantity is quite defective, as opposed to the discrete quantities being the way to look at it.
Yes, there were a number of people following Galileo after Galileo's enunciation of these various things, who thought that actually when bodies fall, they fall at a constant speed for a certain interval of time, small interval. Then the next small interval of time, the speed jumps and they fall at that speed for that, right? If you make those intervals sufficiently small, was argued by a number of people, then you will come up with laws relating distance and time, which from a measuring standpoint are indistinguishable from Galileo's, even though what's going on underneath there are discrete changes.
Mm,
And that
right.
and that was good because it made the discrete change argument more compatible with a scholastic Aristotelian way of thinking.
Right, right. So maybe somewhat along the lines of the paradox, if we take away one, where we add a grain of sand, when is there ever a pile of sand? All those kinds of things. Is it a continual kind of a subjective flux, or is it truly discrete? Can we really parse up experience into little segments?
It's right, but you know, there's no question the ways in which mathematical structures can be applied to the world that we not just experience, but the world that we measure through our instrumentalities and so on, which are after all created by us. They're not parts of our body. We make these things and we make them to do certain measurements and so on. These things are not easy to put together.
Right, right. And it seems there's an element of our choice and volition to so do, to choose the measuring device to parse things up. I mean, that could kind of transition us to, and we could kind of maybe wrap up with the question of whether a so-called theory of everything can be expected from physics, or whether, in fact, as philosophers would claim, the world is best suited for or susceptible to philosophical conceptual analysis, which kind of again gets back to what we've been saying, and perhaps we could say that if in fact we're applying math, we're applying the quantitative onto qualitative experiences, it's not at all reasonable to suppose that results off of that mathematical kind of world image would be metaphysically sound as it concerns a theory of everything.
Well, of course, the two words you just used, one, one is metaphysically and sound, are two words I wouldn't put together too frequently, but the one who pushed the theory of everything most extensively, just passed away last year, was Steve Weinberg, of course. And how shall I put this? I very much doubt that we will ever produce a system so powerful, so comprehensive, so all-encompassing that we will be able from such a system in practice to generate all of the conceivable experiential effects that we could create, measure, and so on. I doubt it. We are, because I think we are ourselves material creatures, there is not a likelihood that we will ever create something that reaches so deeply. But whatever we do create is at least at some level of approximation reflective of whatever it is that goes on down there.
Right. Well, this was a fantasy, right, of, what was it, the 17th, maybe the 18th century? What is it? How do you say, Laplace or Laplace? Laplace of
Laplacian system that, the infinite calculator, if you knew where
Right,
a particle was going, and said, well, we know you can't do that because quantum mechanics forbids it.
right. So it seems
But
that in that regard, that already is kind of a bygone dream. And yet I still think I only use the word metaphysical in a different sense than we may think, in the sense of, is it conceptually conceivable to have such a theory, or is it completely inconceivable? And again, referencing what we've been saying, if in fact we are applying math onto our qualitative experiences, then it's conceptually inconceivable, one might argue, to ever derive a theory of everything from that purely hypothetical descriptive system. Just like we use language to describe our world, and if just by analyzing language, right, this was also kind of a dream of some philosophers, just by analyzing language we can figure out what is right and wrong, what is true, what is false, what is good, what is bad, right? We would say no, language is descriptive of or stand in some relation with our non-linguistic experiences. So if math is a language that describes the qualitative, then it would seem that it's conceptually inconceivable to ever come up with such a theory of everything.
well, of course, yes, it's a language in a certain sense, but it has consequences. And there is, one cannot divorce the development of science and scientific ways of understanding from questions of the creation of instrumentalities and measurement structures and so on. In the absence of such things, you can argue, you can invent all kinds of worlds as you wish, but there are limitations because we go out and we measure. We're not just testing things, we're finding out things too, as we discussed before. I guess I do think that there is some structure to the universe at a fundamental level, which obtains and holds. But do we know, and will we ever be able to fully handle it? I doubt it.
Right. We can keep trying.
Right.
Well, I really appreciate your time, Professor. Anything else you want to add, maybe about just general observations about a lifetime in science and being there at so many fascinating times that are historical?
Well, I mean, I've been around for quite a while, and
Not that long. I'm not saying that, but
but
relatively speaking.
well, things have changed in a lot of ways. In some ways, they haven't. For instance, you could still pick up a copy of Dirac's Principles of Quantum Mechanics, published in the mid-30s, and still learn how to work quantum mechanics at a basic level. Obviously, the development of elementary particle physics and so on subsequently has changed, but it works within that framework still. Now, that's nearly 100 years ago. And I can tell you right now that if this were 1936, nobody would pick up a physics text from 1836 and try and learn anything from it. So in that sense, actually, I think physics has changed less in the last nearly 80 years than it had in the several hundred years or in the previous 80 years.
Is that a negative judgment onto physics, that it's not
No.
making sufficient progress, or a positive judgment that it has?
It shows that they're doing pretty well.
Right. If it sticks, we stick with it. Right.
Right.
Well, Professor, I really appreciate your time. It's been a very interesting conversation. Thank you so much, and I wish you all the best.
You bet. Bye-bye.
All right.